Okay, everybody, so this little video is going to try to explain a bit more how to interpret your data from the lab that we did on water on a penny. So your task is to create a graph that looks something like this, although you'll be hand drawing it. You still want it to be neat, the lines need to be straight, so you're using a ruler, it needs to have a title and labels and all that stuff. But it's easier for me to show this to you using this created on Google Slides or Google Sheets. So in order to understand what I'm going to talk about here, you first need to have calculated the mean number of drops, the average number of drops that water had on the penny, that soap had, and alcohol. So you'll use all the data and you'll get an average. Now, I modified it a little bit so that my averages weren't exactly what you should receive, but I got 26.42, 16.16, and 24.42 or something like that. Those are my averages. But for this class, I'm going to ask you to do more than be able to tell me what the average number of drops are. Because if this was all the data you collected, you would have to conclude that water holds the most drops, followed by alcohol, and then soap on average, right? But there's more to the story. And to understand the extra part, you need to understand two concepts: standard deviation and then standard error of the mean. So standard deviation, we need to think of data in terms of a bell-shaped curve. And what a bell-shaped curve tells us is basically how much different are all the pieces of data. So for the water, we had people getting as few as like 17 drops on the penny and as many as 38. And so the extreme ends of any experiment, right? We didn't get a lot of 17s. We didn't get a lot of 38s. Those are going to be on either end of the bell-shaped curve. The mean tells us what the most likely number is of all the data. So the average of all the data, if you put them all together, and you divide by the total number you did, like what was the middle point of the spread of the data, right? So the middle of your bell-shaped curve is your average, and then different distances away are referred to as 1 standard deviation, 2 standard deviations, 3 standard deviations, and so on. And in biology, we're generally concerned with the likelihood of something falling within 2 standard deviations of the mean. And what I mean by that is, if you dropped water on a penny, 20 times like we did in class, and then you said, all right, I need to predict the next time I drop water on a penny, how many drops am I going to get? And if your average came out to be 26.42, you would say, well, I predict I'm going to get about 26 drops. But what if you did it and you got 23 drops? It's not exactly the mean, but is it still close enough to the mean? How close to the mean is it? And we say that 68% of all of the next pieces of data, the next time you drop water on a penny, 68.3% of that data will all fall within 1 standard deviation of the mean above or 1 standard deviation of the mean below, right? So the next time I do it, I might get 28, and then I might get 22, and then I might get 27, and then I might get a 29, and then I might get a 23. But all of those are going to fall, 68% of them are going to fall within 1 standard deviation of the mean. 2 standard deviations of the mean tell us that we think that 95.5%, and I think I said 98 in class, but anyway, so it's about 96% of the data. If we did it again, 96% of the time, that data is going to fall somewhere in between 2 standard deviations below and 2 standard deviations above the mean, right? So it tells us how likely we are to get that same result again. And if the data is really varied, right? It goes up and down and it's not consistent at all, the bell-shaped curve is going to be really spread out. So the range of data is going to be really wide. Okay, that's standard deviation. In this class, we spend a lot more time talking about something called standard error, and we graph them with these little error bars like this. Now, you did a whole lab on how to calculate standard error. So you're going to have to go and do the calculations for standard error on your own and get the value. Now, let's assume for a second that I did water and I got the mean, and then I calculated the standard deviation, and then I calculated the standard error. And the standard error, let's say it came out to be 3, right? It'll come out to be a decimal point, but let's say it came out to be 3. That means that the standard error is not the same as standard deviation. Instead of telling me the likelihood of the next data point, it tells me the likelihood of the next time that I get an average. So imagine you're going to flip a coin 100 times, right? 50% of those should be heads. That's the average, right? But if I flip it 100 times, I might actually get 42%, or I might get, 62% or whatever of the flips coming up heads. So standard error doesn't tell us about the likelihood of the next coin flip. It tells us about the likelihood that the next time I flip a coin 100 times, my average will be close to the first average. So these error bars tell us how good is the average. Okay? So let's say you calculated standard error and you got a value of 3. When I went to my graph then, I'm actually going to do this for you right now. I'd have my bar graph, and I would need to add 2 standard error of the means above and 2 standard error of the means below. Now this catches some students. They just say it's 3, so they're like, oh, and I'm going to draw a line, 3 above, and I'm going to draw a line, 3 below, and I'm done. No. In biology, we want 2 standard error of the means, 2 standard deviations above the mean, and 2 standard deviations below the mean. That way we are 96% confident that our actual answer is going to fall somewhere in between those 2 points. And 96% confident is good enough for biologists, right? That leaves room for whatever, a 4% chance that it's going to be something different. Oop. Gotta get back to my, there we go. If our standard error of the mean that I calculated was 3, you'll obviously get a decimal point, but let's say it was 3. I would then need to go to my line, and I would say I'm going to go 3 above, so 26.42, so that would be 29.42, but I want to go 2 standard deviations, so I would need to go up to 32.42, right? And I would have the line go down to 20.42. So it would go above the line 2 standard deviations, 2 standard error of the means, and below the line 2 standard error of the means. And now that says that, hey, look, if I went and I did water another 20 times, I dropped water on a penny 20 more times, and I got the average, how likely is it that the average is going to fall between here, or it's 98% probability that it's going to fall between here and here. It tells me something about how good my first average was. Okay, now that's how to make the graph. I'm going to make a separate video for how to interpret the graph if you felt like you struggled to do the to evaluate the data after you had made the graph.